Hello, so in this video we will talk about divide and conquer recurrence relationships. Um, the general form of divide and conquer relationship is given by we have a function, and this is given by some constant times f of n over b plus some other function here. So what this means is that we have our job is to evaluate this function f of n. So what we do is at each step we divide this function into smaller functions so that this is easier to evaluate than this guy, and then there is some constant that this number of functions are there when we divide f of n like that, and this is some extra work we have to do when we divide uh, our main function into a smaller function. Okay, so again we have f of n, then we divide it into a smaller functions, and each smaller function is of size n over b. Okay, and then this g of n is some extra work, so we keep on doing it until we get something f of 1 or f of some constant, which is very simple to evaluate. So in this way we can divide the problem into smaller parts, so divide here, and the conquer relationship is when we solve the smaller problem. Okay, so we divide it into such a problem so small that it is easy to conquer. Okay, so this divide and conquer relationship is used extensively to analyze algorithms, especially recursive algorithms. So to this end we will check how can we do the complexity analysis of a divide and conquer relationship, recurrence relation. For this, the main statement or main theorem which is used is the Master Theorem. So the Master Theorem, it says that if we have a recurrence relation of this form, that f of n is equal to a times f of n b plus, this is our g of n, which is c times n to the power of some d, where n is a power of b, positive power of b, n is equal to bk, and k is a positive integer, then a is greater than equal to 1 and b is greater than 1, and it's an integer, c is greater than 0 any real number, and d is greater than or equal to 0 any real number. If that is the case, then if a is less than b of d, then f of n is of the order of n to the d. If a is equal to b of d, then f of n is order of n to the d log n, and if a is greater than bd, then f of n is of the order of n to the power of log b of a. Okay, so our job for this video is to prove this Master's theorem and see whether we can make any examples of it. Okay. Okay, so now what we do is we start with the definition. Definition is what we have: f of n, this is equal to a times f of n over b plus c times n d. Now this f of n over b, I can again write it as a times f over um, a times f of n over b squared plus c times n over b d plus c and d. So how does this come from? Remember, f of n is f of n over b. So whatever I have the argument here, I divide it by b to get this guy. Then whatever I have here, I take the dth power of that and times it by c. So I have f of n over b. So f of n over b squared plus c times n over b d plus c f n d. Now let's simplify this. This is a squared f of n over b squared plus a times c times n over b d plus C times n d. Now let's expand this again. So what is this one? A times f over f of n over b cubed plus c times n over b squared d. Then I have the next two terms plus a c n over b d plus c n d. Okay, now this guy is a cubed f of n over b cubed plus a squared c n over b squared d, right, plus a times c n over b d plus c times, now this is c to the c times n to the d. Now I'm going to write it as c over n b 0 d. Okay, this will make it easy. Now imagine that I have to do it k times, so I will say, just following the pattern here, so a to the k f of n over b to the k plus, then I will start with a k minus 1, a k minus 1 c n over b k minus 1 d plus, the next one will be a k minus 2, but I will just write the last two terms, a c n over n over b n over b d plus uh, a to the 0. I should have written a to the 0 here as well. A to the 0 times c times n over b to the 0 d. Now let's write it as a summation. So this is equal to a k. Now n is what? N is f. N is equal to b to the k. So a k f of 1. Correct? Plus summation. I is equal to 0 to k minus 1. A to the I. C is there. N over b to the I to the power of d. Correct? Okay, so this is the relation, this is the closed form expression of our f of n. Okay, and this is what we are going to use to prove our Master's theorem. Okay, now let's go to the, so let's write it again. We have f of n, this is equal to a to the k f of 1 plus summation I is equal to 0 to k minus 1 c ai n over bi d. Okay, okay, now let's simplify this a little bit more. So we can write ak f of 1 plus, I can take c out and I can take n to the d out, and then I can write y is equal to 0 to k minus 1 ai over bi d. Or the better way is to write it as k f of 1 plus c n d I is equal to 0 to k minus 1 a over bd I. Okay, so this is the relation which we are going to, okay, simplify more. So what is this? This is nothing but a geometric series. Okay, so the geometric series, the form of this is 1 minus a over bd the power of k divided by 1 minus a over bd. Correct? Okay, so then our relationship becomes plus C and D times 1 minus A over BD to the K divided by 1 minus A over BD. Okay, now we go to our conditions. First condition is what? Let's say A is equal to BD. Okay, so note that for A is equal to BD, this is a problem because this will go to 0. Okay, so we have to go here. We have to go at this place. So for A is equal to BD, then what we do? We say A plus C and D I is equal to 0 to K minus 1. If A is equal to BD, then A over BD is equal to 1. So I can say 1 to the I. So what is this thing? This thing is just equal to K because we have 1's getting added K times. Okay, so this is equal to A to the K F of 1 plus C and D K. So what is K? Now if N is equal to B to the K, then I take log both sides, log Bn. This is equal to K times log B to the B. This is equal to 1. So then this guy is log Bn. So I can say AK F of 1 plus C and D uh, log of Pn, and then A is equal to what? B of D. So we can say B D K F of 1 plus C and D log B of N. So BDK is what? BDK is what? N to the D F of 1 plus C and D log Bn. Okay. Now, which one is faster growing? This one is faster growing, right? Because this has nd times some other function of n. This is nd times a constant here. So this means our function is of the order log b of n. Okay. Now let's play with this one for two other conditions when a is less than bd or a is greater than. So this guy is, if you write it again, f of n, this is equal to ak f of 1 plus C n d times 1 minus a over bd to the k divided by 1 minus a over bd. Correct? So now we have a greater than bd, for example. Okay, but let's not write it right now. We'll write it later. Let's simplify this thing here. So we have ak f of 1 plus let me multiply by bd here throughout. So n to the d, I say bd minus a over bd k minus 1 divided by bd minus a. Okay. Okay. Then I can say this is equal to, let's separate all the terms. ak f of 1 plus nd times c b to the d divided by bd minus a. Then I can say plus or minus c and d. Then I can say a over bd k minus 1 divided by, where by what? Bd minus a. Okay, so what is nd divided by bd to the k minus 1? Remember, what is n? N is, so let's put it here. if we have ND divided by BD to the K minus 1, I can write it as BKD divided by BD K minus 1, or I can write it as BKD divided by BKD minus D, right? So this is equal to BD, correct? So then this guy I can write it as AK f of 1 plus ND CBD over BD minus A minus CA over BD minus A times BD. Okay, AK, right? This was AK. This was AK. Okay, this is AK. Now I can separate this and separate the other two terms. So I can write it as ND times CBD over BD minus A plus AK f of 1 plus CBD divided by A minus BD. Now note that I've changed this minus to plus, but I have also changed the sign of this denominator to A minus BD from BD minus A. Okay, so this is my final form. Now our job is to check the complexity. Okay, now the question is, what is AK? Now AK is equal to what? So we want to write AK in some form of A. So we first of all we write N is equal to B to the K. Okay, which means K is equal to log B N, and A to the K is equal to uh, A to the power of log B N. Now this is also equal to N to the power of log B A. And you can prove it. You can just take log of B on both sides, and this will be log B of A times log B of N, and this will be log B of N times log B of A. Okay, so here we can write it as ND uh, CBD over BD minus A plus N to the log B A times F1 plus CBD over A minus BD. Okay, now the question is about A less than BD, B to the D, which means what? And this means that log B of A will be less than log B of B to the D, which means log B to the A is less than D. Okay, when log B of, so then this means that N to the power of log B of A is less than N to the power of D. Okay, now remember, what is our form? Our form is like this: f of n, this is equal to some constant BDC over BD minus A times n to the D plus another constant which is f of 1 plus uh, f of 1 plus BD C over A minus BD times n to the log B A. Okay, now when A is less than BD, this dominates. When A is greater than BD, this guy dominates. So this means f of n is O of nd because of this term. When a is less than bd and f of n is O of n to the log b of a when a is greater than bd. Okay, so we have actually proved our Master's theorem. So now if you are given f of n, this is equal to 2 times f of n over 3 plus 5. This means your d is equal to 0, your a is equal to 1, and your b is equal to 3. So what is b to the d? B to the d is equal to 3 to the 0, which is equal to 1. So a is equal to b to the d here. A is equal to 2 here, sorry about that. So a is greater than b to the d here. So this means our f of n is O n to the, what is log b? Log 3 of 2. This is how easily you can find the complexity of any function which uses the divide and conquer algorithm and has this kind of a form using Master's theorem. So this is it for this video. Hope it was easy. It was a long one. It was hopefully it was easy to understand. This is important. This is used everywhere. Especially this will give you a shortcut. Tremendous shortcut if you want to use if you want to do some complexity analysis for divide and conquer algorithms. So thanks for watching and hope you like the video.